Have you ever wondered how an app like Zillow predicts the price of a house? Or how scientists determine the relationship between CO2 levels and global temperatures? At the heart of these predictions lies a powerful mathematical tool called ordinary least squares, or OLS. Today, we're going to peel back the layers of complex formulas and look at the beautiful geometry of fitting a line to data. Let's start with a simple everyday scenario. Imagine you are looking at houses in a neighborhood. You notice that as the square footage of a house increases, the price usually goes up too. We can plot this on a graph. The horizontal x-axis represents the size in square feet, and the vertical y-axis represents the price in thousands of dollars. Each dot on this scatter plot is a real house that was sold. Linear regression is the process of finding a single straight line that best represents the trend of all these data points. This line follows the classic equation, y equals beta 0 plus beta 1 times x plus an error term. Beta 0 is the intercept, where the line hits the vertical axis, and beta 1 is the slope, which tells us how much the price increases for every extra square foot. But why is it called ordinary least squares? To understand that, we need to look at the gaps. For any given house, the error, or residual, is the vertical distance between the actual data point and our predicted line. Some points are above the line and some are below. If we just added these distances together, the positive and negative values would cancel each other out, giving us a misleading result. To solve this, we square each of those vertical distances. Squaring turns every distance into a positive value, and more importantly, it penalizes larger errors more heavily than smaller ones. This creates literal geometric squares attached to our data points. The goal of OLS is simple: move the line until the total area of all these squares combined is as small as possible. That is why we call it the least squares method. Geometrically, OLS is even more fascinating. If we think in terms of vectors, we are trying to project our observed data vector onto a subspace defined by our predictors. The best fit occurs when the vector of residuals is perpendicular, or orthogonal, to the plane formed by our variables. In other words, the shortest distance between our data and our model is a straight, perpendicular drop. For OLS to be the most reliable estimator, certain conditions must be met, known as the Gauss-Markov Assumptions. These include linearity, independence, and homoscedasticity, which means the variance of our errors should be constant. When these hold, the Gauss-Markov theorem proves that OLS is the blue, the best linear, unbiased estimator. According to statistics from the Journal of Econometrics, OLS remains the most widely used estimation technique in social sciences due to its simplicity and interpretability. From predicting stock market trends to analyzing public health data, OLS provides a foundational bridge between raw data and actionable insights. In summary, OLS is about finding the path of least resistance through a cloud of data. By minimizing the sum of squared residuals, we create a model that balances every point's influence to give us the most accurate trend possible. Next time you see a trend line, remember the geometry and the least squares working behind the scenes. References: 1. Gujarati, D.N., Basic Econometrics. 2. Johnny Friend, Mathematical Statistics. 3. Woodridge, J.N., Introductory Econometrics, A Modern Approach.